So yeah, today we're going to so last class where we stopped was we defined what was inverse filtering, and we saw that it performs well when you have only a blurred image without any noise. Now we'll see if we can extend this inverse filtering if you add noise, and see that it doesn't work if you add noise, because I'll show you why, and then we'll see a method to go against it is Wiener filter, which is Wiener filter is more generalized form of inverse filtering, so with which you can suppress the noise which arises from Wiener filtering. After that, we'll understand what maximum likelihood is estimation is, and maximum a posteriori is, and then we'll see some simple priors, how we can induce priors onto on an image restoration model. We'll see some kind of toy examples, and then we'll see how to deal with Poisson noise. So ideally, Poisson noise is the kind of the more realistic noise occurring in real life. So, but there are not good ways to go against it. And we'll see one way how to denoise images with Poisson noise. Okay, so let's say we have a clean image which we call it as IXY, and I hat y is a blurred version of image, and the blur is obtained through by convolving with a PSF of HXY. And for now, okay, I said for now let's ignore noise, but let's not ignore noise. Okay, so anyway, let's go forward, and let's say we don't have noise here. So then I'm reminding you, okay. Okay, so then I'm reminding you that how we saw how to filter this is just by dividing by going into the Fourier domain, which is below. Like IUV is U and V are the spatial frequencies, and if you don't have any noise, then you can basically just divide with the Fourier response of the PSF. Okay, let's say no. Okay. Okay, I'm not parameterizing it, but still. So now let's see. Let's recall that. So now I'm setting the problem setting. My blur is motion blur, where the PSF I'm synthesizing here, and my inverse filter was implemented like this. You get the FFT of inputs, FFT of Fourier, and then for some numerical issues, I removed all these zeros to avoid division by zero. I replaced with a very small number. So, and then we saw that this performs well for denoise and it's able to recover the blur. Okay, this is what we saw in the last class. Now let's introduce a little bit of noise to this, and so so basically I'm introducing like a noise with variance of 0.01. So to generate Gaussian noise, I'm using this np.random.randn, which by default gives noise with 0 mean and 1 variance. Now when I multiply with this noise variance, I get noise with whatever variance I want to. Okay. Gaussian. White Gaussian noise, yeah, and I'm giving it a shape. I wanted to generate a specific size of this IID noise samples. So basically, each point is independently, identically distributed. So now let's see how it performs. The inverse filter. You see that it totally breaks. So if you zoom in, you can see that it kind of puts in some random, very high frequency sinusoids. Which means it's amplifying the high frequencies. And by the way, we also saw a way how to get rid of it. What we did was we took a circle and we just cut out all the frequencies outside, so that we are trying to get rid of some noise, but that doesn't always work. So let's see what is happening here. So this is our deformation model in Fourier domain. So HUV is my blur kernel Fourier response, and IUV is my image Fourier response, and NUV is my noise. So let's say my initial Fourier transform of my image is something like this. It dampens, it has some decaying spectrum, and since my blur kernel is also low pass filter, some kind of, so it doesn't have it has some kind of decaying spectrum. So when I multiply with this, you get this black line here is basically when whatever you multiply with the h with f, and then we're adding noise in this Fourier domain. Recall that if you have additive noise in the spatial domain, it's also additive in the Gaussian in the Fourier domain. So since we have additive noise here, when we're trying to apply this inverse filter, which is 1 by HUV, so when we try to invert it on the black line, it goes well and it becomes the blue line. But what happens to this red line is just it when as the inverse of this decaying spectrum is kind of monotonically increasing response, it just amplifies the high frequencies. See here, whatever is beyond this intersection, it's not supposed to be amplified, but it does. So that's why we get such a thing in the Fourier domain, and when we take the inverse Fourier transform, you get these high frequencies. What we saw in the last class was we just did a trick where we cut off at this point. We put a circle and we removed both the images response and the Fourier response and the noises response after this intersection, and it kind of worked. But what we'll see now is it's how to do it properly, like as Alex taught you in the class about Wiener filter. So it's defined this way. So let's this is my deformation model, and this is he derived Wiener filter in the class, which he got by minimizing the MMSE of this forward model. So basically it's defined like this. It's H conjugate of U and V, and it's divided by the absolute value of this Fourier transform plus some K, and this K is basically the PSNR, not PSNR, it's SNR. So what it also means is it's just the ratio of the PSD of the power spectrum density of noise divided by the power spectrum density of the image. So when we do that, you get so this is our hyperparameter whenever we apply the Wiener filter. This is the hyperparameter. We provide the Wiener filter, the blur, since it's not blind deblurring, we provided the kernel and this K. So and after that we get this filter, and then we multiply it with the degraded image, and we expect it to improve, right? So if you notice carefully, then if this K goes to 0, which means there's no noise, this is the same as what we had before, which was inverse filtering, and if there is heavy noise, that is the K is greater than much greater than the other term, the high frequencies are attenuated because it's in the denominator, so it's attenuated. So let's see. So in practice, both you have some estimate of your PSNR, like how much noise is added to your system, which is not completely true, but you have some kind of an estimate. So you plug in that as the K, and you have this I hat as you also know the I hat, which is your degraded image. So you see what's happening here. So this is my original image. Sorry for the notation. It's F is supposed to be I. So I is my so I is my degraded image, and now I want to no, it's the opposite, sorry. I is my original image, and the deformation model is defined as it's multiplied by a kernel H and added noise N. So basically when you multiply with in Fourier domain, it's just multiplication with a decaying spectrum of blur kernel, you the black line is basically like we saw before. It's supposedly the degraded the blurred image, and when you add noise to this, and this W has a spectrum something like this. So until when the noise is huge, it kind of dampens the weight. So basically, if when you have a uniform noise throughout the spectrum, it gets dampened like this. Instead of cutting off, it just some nicely dampens the spectrum. So when you recover it, you recover all the frequencies correctly. So let's see. So let's see how to implement it. It's very simple. So here I take my image, I have my kernel, and I have this my k as the hyperparameter k. You just take the image and you take the Fourier transform of it, and then you take the Fourier transform of the kernel, and you just there's this function called np.conjugate. It basically calculates if it's really since it's a FFT, so it calculates the complex conjugate of this h, and you can and then you divide by this, right? So this is basically calculating this. So you take np.conj of this and just np.abs of this squared and plus k. K is something that you provide. So let's see how this performs, and then we invert it, and then we align it with FFT shift, and you get the final Wiener filtered image. So again, I'm taking the motion process with I'm moving my motion of my camera along one axis with length 10. And then I'm blurring it with this kernel and adding noise here. So then I get a noisy blurred image, and then I'm doing a Wiener filter to restore this, and I gave 0.01 is my noise variance here so I'm giving it as the parameter for the Wiener filter. So let's see how this is. This is my blurred image. This is the response of it, and then this is the one with noise. You can't see noise here, but I can show you. So this is the noise that I was adding to this image from this image. So, and then I recovered with my Wiener filter. You see that it's recovering it quite well when compared to the previous performance of the inverse filter. So it's actually dampening the high frequencies. So it's nice. So any questions?
Again, about the noise.
Yes.
You're saying the noise is like all the spectrum.
Yes.
But you said it's like Gaussian noise.
Yes. It's not Gaussian blur, it's Gaussian noise. I think you're confusing it. Yes. So it's white noise. So it's white Gaussian noise. Yeah. So if because it's sampled from a random normal distribution from a normal distribution with mean 0 and variance 1. So it's white because the covariance of all the samples is it has an identity matrix. Yeah. So it's it performs quite well. But this is so this is the Wiener filter. Now we'll look at what is the notion of maximum likelihood versus map estimation. Okay, let's say my degradation is modeled like this. H is my blur. So H is my blur kernel, and N is my noise. So in maximum likelihood, what we have what maximum likelihood does is you have a parameterized set of models for you. So what it does is it picks the maximum, it picks a particular by parameterized set of models, I mean my set of images, which are all the possible solutions of this, of the recovered image. So from this whole set, I'm picking the one which maximizes, which fits our data well. So that is maximum likelihood, and in the very subtle difference, but in map estimator, what we're trying to do is we try to maximize on the posterior distribution. So we try to pick a model which maximizes our posterior distribution such that we get the data. So although the difference is very subtle, the impact is really huge, because you can, when you actually maximize the posterior distribution, you can use the Bayes rule and you get this term. So instead of in ML estimator, you basically maximize when you have you get the probability distribution function of this I hat, and you try to find the particular I tilde which maximizes this probability distribution. In here, you actually assume that you know the model and your data came from it, but you actually don't know the model, so you use the Bayes rule to get rid of it, and you try to maximize and you try to maximize this one. So here if you notice, the first term is already maximum likelihood, and the second term, which is since you can get rid of this term because it doesn't affect the maximization, so it's something close to naive Bayes if you have learned it in machine learning course. Also, it has many resemblances to machine learning, and also in optimization when you do constraint optimization. It's basically you're saying that, okay, let me finish this. So here what we end up with is so my maximum likelihood plus multiplied by something else, which is my prior term. So how it relates to machine learning is, even machine learning, this let's say you have a linear regression problem, then one way to find the solution is to just maximize over all the parameters, but another way is you can actually say something about the model through regularization. So this is some kind of a regularization. You're adding that, okay, my model performs like this. Or in the image processing scenario, you can say that, okay, my recovered image should be smooth, or should have edges, or should follow some nice property, something like that. So it can also linking it to optimization, what it does is you're trying to search in a constrained set of images. Let's say I enforce my prior to be smooth. Okay, I enforce it somehow. Then basically you're looking in all the set of smooth images, like which one is closest that satisfies my MSE by maximum likelihood. Which one among this set is closest to my estimate. So in some sense, you can also think of it like approximation error. So you're looking in, you're basically constraining the family of functions that you're looking at, and the first term is your data fidelity term. It says how close you are to the original image, and the second term says what kind of functions, what kind of images should it be looking at. Let's say you have a bad prior. Let's say you say that all my images should be super sharp. Then essentially you will end up with a super sharp image, but it's not the fault of it's not the fault of this term. It's the fault of this term. You modeled your function differently, so it will end up with that. It's like an active constraint that acts on this. So let's see it in a deconvolution setting. So let's say we have this degradation model. So I mean, it's basically this, but it's this. I put the noise on one side, and so essentially, what is P I hat, P I cap, or I hat, whatever. So basically, in this term, this is not random. This has no probability distribution. The only thing that has distribution is this one, which is random Gaussian. So my probability distribution function of P I hat is basically the probability distribution function of n, where the random variable is I hat minus hi. So when we put this into it, so you get this is like a multivariate Gaussian distribution, and CW W inverse is my covariance matrix. So if my Gaussian, let's say like my noise is wide Gaussian, so this covariance matrix is nothing but an identity, which is scaled identity, and this, let's say the scale is beta. So basically, this you're trying to now what you want is you want to find an I such which maximizes this probability distribution. So with some simple elimination, you can just take maximizing this is also equivalent to maximizing the log of this, because log is a monotonic function. So you just get rid of this exponent, and you just maximize this one. I mean, basically maximizing the negative is it's minimizing. You're trying to find a minimum I which satisfies this. So with partial Wahl's equality, you know that you can just take everything to Fourier, and you will end up with something like this. This is the Fourier, IF is the Fourier transform of I hat, HF is the Fourier transform of H hat, and so on. Okay. So, and we saw that what we want to find I such that it this is supposed to be IF. Sorry. Yeah, we want to find such an IF which minimizes this equation. So it has a closed form expression which is exactly the inverse filtering. It's basically IF minus I hat f by I HF, which is just dividing the inverse filter, dividing my degraded image with the Fourier of my PSF function. Okay, so we know that it's bad. We saw before, like, this solution is not good. One other way how you can do this is you don't have to go to Fourier domain. Let's say you don't have to use this Parseval equality. You can just minimize this. Then basically what is your I? It's just H inverse of I hat. But since your H is like huge dimensions, so it's difficult to invert it. Also, if the inverse doesn't exist, you have to take the pseudo inverse. So it's simpler to do it in Fourier domain. So there's a good chance that the Fourier transform, the inverse of H doesn't exist, because H is our blur kernel, and most of it is 0. So you can take the pseudo inverse. Essentially, you will get the same answer. So in a map setting, so I'll take an example and explain how you can do this. In map setting, if you recall, this first term is your maximum likelihood term, and the second term is the prior, right? So instead of maximizing this, you would like to maximize this. Let's say for now I consider that my images are smooth. So I want to induce such a thing into my prior. So how would I do it? So let's enforce some smoothness prior into the image. How do you do it? So you can just assume that let's say I have my image which is multiplied by the kernel. I mean, not multiplied, but which is convolved with this with a sharp kernel, is distributed around 0 with some variance. So let's say P is my let's say Laplacian kernel, which is something like my which has more need to draw it somewhere. Okay, it looks something like this. I'll show you. No. Okay, let's say this is my kernel, right? So what do you get? I mean, what we want to say is when you multiply this with when you multiply this with my image, it has to be a small Gaussian distribution which is surrounded around 0, and you can control the variance with the sigma p square. Okay, so that's how. I mean. So how can you know that this enforces smoothness? Is the image get punished if it doesn't have if it has any sharp edges, so it will have high response when it's multiplied with this filter. So whatever so when you want to find the when you want to get a minimum value, so this basically stops from getting it. So that's how you enforce it. Like it's kind of like regularization in kind of machine learning terms. So you can convert this probability function into this. Okay, the first part is your data fidelity term, which means my maximum likelihood term. So you want to minimize this such that you have some kind of a regularization saying that I want to also minimize this along with that. Since both of them are Gaussian distributions, I can just multiply them in the exponent, and eventually I'll get addition when you take them down with log. Okay, so again I can use Parseval's identity, which says something like this. Okay, so then I expand this as this matrix product, and yeah, so essentially I end up with something like this. Okay, so I mean this I expand this and I minimize with IF. I mean I want this equation to be minimum. I want an IF which minimizes this energy, let's say. Okay, so the IF that you get is basically multiplying. So here I did some mistake. So multiplying this whole thing with I hat, right? I hat of f. Okay, so what I got was I want to I want to basically find the it's HF conjugate divided by the same thing as we got in the Wiener filter, if you remember. So the Wiener filter plus what extra we got was, instead of k in the Wiener filter, which was what we were tuning, we got a regularization term here. Okay. So this can be otherwise solved using in the spatial domain. You can just expand everything and just minimize with I. Basically, you have to take pseudo inverses there, but essentially you'll end up with the same thing. Like you'll get some kind of a similar metric. Basically, what you might get is H transpose H plus some lambda. Let's call this lambda times. Let's see. I'll write it down. Oops. So if you do it in the spatial domain, you'll get something like this, right? No, did some mistake. Nope. Never mind, I'm not taking the risk. So basically what you get is H transpose times all this matrix except without the F's, and then you get the inverse there, and then you multiply with the spatial response of the actual image. So you can do it either way, but doing that requires huge matrix inversion, so you can simply do it in the Fourier domain with by just dividing element wise. Okay, so let's see how to implement this. So what I did was, so I took two examples. First one, let's see the first one. So in the first one, what I'm doing is I created a motion process, and then I blur it, and then what I'm doing is I'm adding noise, and then what this function does is it just implements this, very similar to what Wiener filter did, but what it does is I created this P matrix here, and then I'm taking the Fourier transform of it, and just merely writing down what I wrote there. So you get this, and then you multiply with it. So
how did you decide what P is?
P. So for example, that's what I was explaining about smoothness. So if you want to force your image to be smooth, you have to punish it when it gets to high values in the edges. So that's why I'm minimizing this distribution. So what is this distribution? My P is a sharpness kernel, like it gives my derivatives, and if I has derivatives, if I peak on wall with I has strong derivatives, this gets a high value. Okay, so you want to minimize that. Okay, is it clear? Yeah. So yeah, so that's why I chose. If I want to enforce smoothness, I choose a sharp kernel here. Let's say I don't want to enforce smoothness. I want to enforce the edges. So I punish it when it gives a smooth response. So now I give it a smooth filter, like a uniform filter, and if it gives if it has high response for it, you punish it. So you get some kind of a sharp image. I'll show you in the examples. So essentially, implementation is pretty straightforward. Like it just writing down whatever is here, and the key thing is I took my P here, and then I took the Fourier transform of it, and I wrote it down. That's it. So let's see how this performs. First, I'm showing you the how it. So this is my deblurred image with using this smoothness constraint. So I'm not sure what you see here, and if you can appreciate it when compared to Wiener filter, but I'll show you what happens when you do the other way. So when you do, let's say you enforce instead of enforcing the smoothness, you enforce the sharpness. You can see that it's significantly the edges are much sharper here. Look at the hair. It's smooth. It's smooth in the top, and then it's much sharper here. So this is one way of regularizing, right? So what to remember is right now we are finding these are very simple priors for which you can have a closed form expression. So it's not always this easy, but this is the one of the primitive priors.
In general, you choose P according the attributes you wanna.
Yes, exactly. So you want to force what you want in the image. So you are constraining the function space only to look at all the possible sharp functions, or all the possible sharp images, which has high response in this filter. And you're picking the one which minimizes the most your data fidelity, whichever is the closest. Let's say you have all your sharp images here, smooth images here. The whole thing is your space, right? So let's say this is your MMSE estimate. This is your Wiener filter. You're picking the image. When you enforce the sharpness constraint, you're picking the image from this set, and you're finding the closest possible thing to the Wiener filter. When you enforce sharpness, you choose from this set, and you find the closest thing to this. But you can't go beyond this because this is an active constraint. You can't escape this. So also you can enforce how sharp your image the image you want through this lambda. So if you notice, you can, let's say if you control this variable saying that okay, I want my image to be really sharp, so you just increase it, so it constrains it more, right? So yeah, that's it. And now we'll look at something different. So how do you do Poisson denoising? Last class we saw what is a Poisson noise. So in low light conditions, when photons doesn't hit your sensor, the way that they hit the sensor follows a Poisson random process. So we simulated how the noise looks like in the last class. I'll show you briefly now. So, and then if let's say you want to do all the things that you said above for these images. It just doesn't work because we started with the basic assumption that our I hat all our possible images are distributed in a Gaussian distribution, but which Gaussian makes life easy, so that's why you did that. So since we took Gaussian distribution, we were able to simply take the log and bring the mean squared term down and just find a simple solution that can be invertible. But let's say it's not so easy. Then so what do you do? So this Anscombe transform is a variance stabilizing transform. So there are many of such heuristic methods, but one of it is Anscombe. It's also famous. So until 2012, any method which proposed to do Poisson denoising basically did the same thing. They convert they take your original image, they convert it into some transform domain. Basically, you can convert any random variable to any random variable using some transform. So you just take a Poisson distributed image. You take you apply an Anscombe transform on it, so it becomes quasi Gaussian. Not exactly Gaussian, but I mean it's more or less Gaussian. So you apply whatever you know, like your best denoising method on this transform domain, and then you do the inverse Anscombe transform. It's pretty heuristic. It's defined like this. So it's Z is my image. So you just add this 3 by 8 and take a square root of it and multiply by 2. So and then you do the opposite when you get back. Okay, you do all the filtering operations by adaptive Wiener filter. I meant this constraint least squares that we did, like you constrain it, enforcing the sharpness and all this stuff. So let's see how you can implement this. It's pretty straightforward again. So you just add 3 by 8 and delete. There are some heuristics here. So this is one possible way of inverting it. There are other methods also. It's not really important. You can always look them up. So some perform well than others, or something like that. I'm not really sure, but I mean this is not all I want to emphasize is this is not the only inverse Anscombe. There are some methods. It depends on how much how the distribution of an image looks like. Let's see how it looks like. So initially my histogram was this of my image okay, so my Poisson noise here has a peak value of 20. So you see that after 20 it basically dampens very, very sharply. So this is my Poisson noise image. All my pixels are between 0 to 20 integers. So then when I do the Anscombe transform, it kind of pushes all of them to so maybe you can see it better if I remove this. Say 50. So you see it kind of Gaussianizes the original heavy kind of almost exponential this Poisson distribution. So here you do whatever you want, like Wiener filter or adaptive Wiener filter, whatever you want. So and then you take the inverse Anscombe transform. So what I'm doing here is basically I'm applying Wiener filter here, and then I'm taking it back, and you'll see the resultant image. And what else I'm doing is I'm also enforcing this Laplacian constrained least squares. So the P thing I showed you before, this one. So let's see how these both perform. So this is my original histogram, Poisson histogram, and then Anscombe transform. So this is my let's see, I don't remember. This is my Poisson noise image, and so basically you see that it's Wiener filter is almost doing nothing here. So I mean I don't see much improvement, but you can see some pixels are different, but it's not doing much. But when I apply this filter that we talked about, the enforcing the smoothness on the image, you see that it's actually doing something. It kind of recovers. This is my original Poisson image. It's able to recover this, right? So it's kind of nice. Not the best, but still. So after 2012, 2014, and all this stuff, what people do now is they just use neural networks, CNNs, just input. So what is the advantage of the CNNs? You think about it. So if you have when you're inducing such priors, mostly you don't know what probability distribution your actual natural images look like. But what CNNs have advantage is they can approximate any possible function. So they basically have zero approximation error. All they have is optimization error, which is still a problem, but still, I mean, you got rid of all the approximation capabilities. They have very good capability to approximate almost any kind of function. Like it's proven from settings, and yeah. So basically this PI this thing you're getting rid of, and you're putting just a CNN which will do, and then you just have to minimize this one. You give it I hat and you give it I. You show it 1000 examples and it will do it. Since your network has the capability of approximating it. So recent low light denoising, there were a few papers. One of them even from our lab. What they do is they just took a aligned dataset of an image which is taken with very very high shutter rate. Basically, you're taking 200 images per second, and you're collecting the same image at very high shutter rate. Very low shutter rate, basically, which is basically you're collecting all the light. So essentially you have an image with Poisson noise when you have high shutter rate, and then low shutter rate you don't. So you just build a CNN which regresses from here to there, and it works much better than this Anscobe transform and all these transform domains which were explored, which were shown to be decently performing until 2013 so this is one of the significant advantages you get while using CNNs. Now until now we saw the priors only which can be invertible. Like you can just simply do some filtering in Fourier domain or in the spatial domain, and you can get the filtered image. But mostly the priors which are famous, the ones which are in 2000s, which were mostly discussed in 2000s, like the sparse priors or patch-based priors, all these priors don't have a closed form solution. So you have to solve some optimization problem using some first order methods or second order methods, and then you get such so-called degraded the denoised image. So we in the future classes we'll look at one such example, like how to induce sparsity on an image, like not an image but on a patch. So let's say you have this image, you break it into patches, and you say that each patch is built from a dictionary of atoms. Like each patch is a linear combination of certain number of atoms, and apparently it's a really good prior. It performs really well in denoising and many image processing tasks. So we'll look at more of these priors and and how to solve these optimization problems probably in the next class or the one later. Yeah. So yeah, that's it.